do a little bit of speculation about denotational semantics. And I was in a class, denotational semantics, in 1981. The lecturer was more or less saying that concurrency was maybe a problem, and it didn't make any sense to me. The concept of concurrency being a problem for denotational semantics didn't make any sense then, it still doesn't make any sense now. So I wonder what people are saying when they say that the difficulties with concurrency. I think what they're saying is that you can use denotational semantics as a Turing-complete system. You can use it as a programming language. I don't think there can be any doubt about that. I'll have another look at Schmidt's book. I don't know whether he actually suggests using it as a programming language or not. But, I think it is a programming language. Schmidt points out that you've got data for a program. The data is in the programming language. So I don't think there's any doubt that denotational semantics, being a description of a programming language, is, if it's a description of a programming language, well, that itself is a programming language, surely. Well, it's a language anyway. Let's call it a programming language. I'm just wondering if there's automatic ways to translate between these different descriptions. In the case of finite state machines, I don't think there's any doubt about it. If you've got some logical expression, you can optimize it in some way. Probably optimize it in different ways. For example, produce an implementation with a minimum number of components, say, given a set of components, a library of components that you're drawing from. Implement a lowest cost implementation and so on, given a library of resources that you've got to work with. Should there be any difficulty in doing that for things that are more complex, for things that have infinities in them? Should there be any difficulty? I think we can hypothesize that there's no difficulty in doing it. And maybe it's a lifetime's work, maybe it's many lifetimes' work to actually come up with evidence for that fact. For example, we might want to come up with some denotational description of, let's say, a statement of Fermat's last theorem. And we're making some claim that a digital computer or something can be used, that it can be possible to program a digital computer to come up with a proof of Fermat's last theorem. We might be a long way off yet from producing that. But even if we are we any worse off than what's being done in the computer industry, where people are seeking funds for huge projects with many staff working on it, people writing code? Is it any worse what we're doing than attempting some project? Maybe that's about all I've got to say at the moment, but there's a couple of papers I want to read. One is by Philip Wadler. He said that it's wrong to say that you can't have assignment with a functional language, but at the same time he said that there was something a bit strange about, I think he was saying there was something a little bit strange about assignment in a functional language. I think he was saying that you can't duplicate the world. Well, I think you want to be able, and you can't destroy the world. I think you want to be able to duplicate the world and destroy it. And what I'm talking about here is virtual reality models. And the world that you're talking about might be some very tiny construct, such as Kripke might have invented. So this seems a very important part of your theory, is that you do want to be able to destroy the world and copy it. Unix, for example, you can copy a process. very simply, and presumably that process could be arbitrarily complex. Could be as complex as an arbitrarily complex world, one might imagine.